it goes through a channel h of t, additive Gaussian noise distorts that signal, and the output is y of t. Okay, well, it'd be really nice, and we've already seen that I could replace this channel with xbb on the input, so I could write below it xbb. Okay, what I'd have to do here is 1/2 hbb of t, which is just take the Fourier transform, move it down to 0, don't multiply by 2 in that case. I know the noise that's added here is going to be some complex noise, so that has 2 n naught. Delta of t is the autocorrelation function, or power spectral density is 2 n naught. And then over here I've got y bb of t. So that's what that's going to look like, this system. All right, this is great for analysis. How do I actually get the y bb of t in the receiver that corresponds to this particular analysis, which I've taken off to the side? I'm going to analyze the system. I'm going to do it with complex functions. Okay. All right, well, great. Well, where are the complex functions inside my receiver? Everything's real. Yes, sir?
Sir, I'm not sure what complexity are we taking out by doing the baseline analysis? Like, is it just carrier frequencies and everything?
The carrier frequencies are removed, and I get PAM and QAM in the same analysis. So I don't have to have a separate analysis for each this way. So that's the reason, is to get PAM and QAM. We're gonna learn how to design equalizers, which are basically going to be transfer functions, if you will, linear systems in the receiver that are going to try to undo the distortion in the channel. And I'd like to be able to do it for both PAM and QAM, and I don't want to introduce 2 different analyses. So by doing this, I get one analysis that covers them both. Okay, so this is the objective. Now let's see, how do we actually get there? So let's talk about generation of YA of t and YBB of t from y of t, because what we really have is y of t. So I start my receiver with y of t. It's not too hard to fake an analytic signal. What would I do? Well, inside my processing inside the receiver, I'm going to have 2 paths. One will have a Hilbert transform. The other will have nothing. And I'm going to pretend on this second path, which now has the Hilbert transform, that I've multiplied by j, square root of -1. How do I do that in actual implementation? Well, I have 2 paths. And if I'm going to do complex arithmetic, I know how to do that, but essentially complex arithmetic deals with 2-dimensional vectors. And those vectors have a real part and an imaginary part. And I can proceed to analyze everything in that way. So I can think of adding these 2 together to become a complex signal. In reality, there's no addition. I simply have those 2 paths in my receiver. But what I will have here is YA of t. So I have generated the analytic equivalent. Notice that by taking the signal and basically replicating it here, once through the Hilbert transform and once without the Hilbert transform, in some way I've kind of erroneously doubled the power of the system, because I've got the signal here, y of t. It happens for both the noise and the signal, so no harm done. But artificially, there's a factor of 2 in terms of power increase, because I've got these 2 paths receiving. Hilbert transform does not change the power. If you remember, its magnitude in Fourier transform is 1 everywhere, so it does not change the power through it. Then what happens is, in complex arithmetic, I can write it this way, but of course, what happens is it's really 4 real multiplies. I've got a real and imaginary part here, which are cosine and sine of omega ct. And I multiply the real part times the real part, and then the imaginary part times the imaginary part of these 2 complexes, add them together, and I have the real part of the output. And similarly, I take real times imaginary plus imaginary times real, and I've got the imaginary part of the output. So I have in effect, a complex signal right here, and this I'm going to call y tilde bb of t. It is y bb of t, but I'm going to put a tilde there for a reason that will become clear later. So this particular device in signal processing is often called a phase splitter. Takes the signal y of t and splits its phase into a real and imaginary part. Modulates it down to baseband. Okay, produces this baseband equivalent, which now, okay, is essentially what I have up here in this system. So I found a way to actually generate. I can analyze the system, and I could actually implement any kind of receivers I come up with later for complex signals. I could implement them on the two dimensions here of the QAM signal. And if it was PAM, just throw away all the imaginary parts, and I implement just with a single real signal. Instead of having 4 multiplies for each complex multiply, I have only 1 multiply if I have only real signals involved. Now, yes, sir. Could you use the mic? Actually, I got to keep reminding people. Sorry. No, it would not. It would not actually be anything, because it would just be I'm going to call that my pretend path, my imaginary path in the receiver, which corresponds to the imaginary part. And what are the two operations we typically do in signal processing are add and multiply. So adding is easy. You know, you add the 2 real parts, you add the imaginary parts, you still have a 2-dimensional quantity. Multiplying is actually 4 multiplies and 2 adds to do a complex multiply. Okay, so this system kind of artificially doubles power, which I noted just a moment ago. So really I have 2 times y, because I've got it on both paths, which produces 4 times y squared. So there's a doubling of power in effect that occurs in this system. Now, but this is, of course, only at positive frequencies. So it is true that I could think of that power being quadrupled at the positive frequencies, but because I don't have the negative frequencies anymore, it's only double the power in a system. So what I'm going to do instead, well, let me just point out before I say that both the noise and signal undergo this type of processing. So if I've artificially doubled power of the signal, I've also artificially doubled the power of the noise. So in effect, the signal to noise ratio hasn't changed. Okay, so it's not like I've improved my system by just some kind of wizardry where I take the signal and use it twice. It's not happening. Yes, sir. Microphone? Thanks.
So is this process linear in that sense?
This process is linear. It is time varying because of the demodulator, though, so it's not linear time invariant. Now, it's actually figure 2.8 in the notes, which I'll call your attention to. What I do there is, instead of just using the phase splitter above, because of that artificial doubling of power, I multiply the signal amplitude itself by 1 over square root of 2. So in power, I'm dropping by 1 over square root of 2 squared, which is 1/2. So I'm resetting the power to the original level. And then I go through the phase splitter, which I'm going to abbreviate PS because we just drew it earlier. But that's the thing, Hilbert transform in parallel with the signal and then multiply by e to the minus j omega ct. And now, that output, actually, let me come back in my notes here. I want to correct something I said. I put a little tilde here. I looked ahead in my notes and drew it on the wrong diagram. Erase that. That is y baseband of t. Just stay with that on the earlier diagram, because I'm with this 1 over square root of 2, that's what I'm going to call y tilde bb, because it's got this additional scaling of 1 over square root of 2 involved. And of course, I would only do a phase splitter and the associated multiplication by 1 over square root of 2 for QAM. if I had PAM, I don't have to worry about any demodulation or complex signals. I don't have to worry about any artificial scaling, so I'd not put this in. So what I do is I take the phase splitter that's common in communications, and I just put the 1 over square root of 2 out in front. And what this will do is it prevents some kind of artificial doubling of both noise and signal. It's correct that that doesn't change the performance at all in the system. So I could have left them in, and that's what would actually be implemented in practice is this phase splitter. But for analytical purposes, I'm going to introduce this. And what is that going to do? Well, as we'll see momentarily, it's going to make the power levels, the absolute power levels of the signal and of the noise consistent on a per-dimensional basis with the PAM system. So to avoid some confusion because of this artificial doubling in analysis to come in subsequent lectures, I introduced this scale factor, which you can always put in the receiver. You don't really have to do it in practice, but what it does is it's going to get rid of this artificial doubling of power. So what I will have then in terms of the equivalent system, so I have this 1 over square root of 2, okay, that is touching both signal and noise here in y of t. So if I were to draw the equivalent channel, I'd have an x tilde of bb of t, which is the baseband equivalent t, divided by square root of 2, processed by same channel we talked about earlier, h of omega plus omega c. That's just taking the original Fourier transform, moving it down to the origin. This is 1/2 the baseband equivalent here. And because I have this 1 over square root of 2 affecting both signal and noise, I push that into the noise. So I'm going to have an nbb of t divided by square root of 2, which I could also call an n tilde bb of t. And that's what produces my y tilde bb of t. When I have this phase splitter with the 1 over square root of 2 in front, that's what this produces. So that's my equivalent complex system. Okay, let's look at what that does to both the signal and the noise. And you're going to see that this is very convenient, removing that extra factor of 2 of power. On the noise, we had 4 times the power, at least the power spectral density, I should say, at positive frequencies. So SBB of F was equal to 4 times Sn of F plus Fc, which was equal to 4 times N naught over 2 for white noise. But if I had instead 1 over square root of 2 NBB of T, then I have an extra factor of 1/2 in terms of power because I square this. So my SBB tilde of F, if you will, is going to be 2 times Sn F plus Fc, which is 2 times N naught over 2. Now that's pretty convenient for a complex signal because what's happening is this is a 2-dimensional entity. It's complex. It has a real part which is 1 dimension and a complex part, imaginary part, which is the 2nd dimension. So if I were to normalize this, let's just call it SBB of F bar, by the number of dimensions, it's N naught over 2. So per dimension, because of that scale factor I put out front, I have exactly the same noise variance and PSD that I had earlier in chapter 1, okay, which was always N naught over 2 per dimension and equal to the power spectral density. So that's convenient. Noise looks just like it did in chapter 1. All I have to do is use this scaled version of the phase splitter, and my analysis follows with noise looking exactly like it did on each of the 2 real dimensions, which are the real part and the imaginary part of the complex noise. As far as the signal is concerned, x of t, you remember back from 2 lectures ago, we talked about the QAM signal, which looked something like this. It had a first dimension times a square root of 2 times phi of t times cosine of omega ct minus a second component from the constellation, square root of 2 phi of t times sine of omega ct. And those square root of 2's were kind of annoying earlier because basically they were there to make the basis functions orthonormal so that they all had unit energy. But what's going to happen, of course, with x bb tilde of t is I take this part here, divide by square root of 2, so I'm left with x1 phi of t. Should have a, well, and then I look at the part that multiplies minus sign, so I have plus j x2 of phi of t, and in fact, I could write this as x1 plus j x2 times phi of t. And it looks a lot, remember I said any basis function, any basis function we use for PAM that we kind of liked could be used in the QAM modulation functions. Well, here I have a very PAM looking type signal, except it has a complex multiplier out front where I take the constellation point on the horizontal axis, and that's the real part, and I take the constellation point component on the vertical axis, and that is the imaginary part. So that's kind of convenient too, because back here in my diagram that I just had, this simplifies to just take one of the dimensions plus the other dimension, okay, and times a single real basis function, phi of t. Oh, this is real, but this is complex. Okay, and then that proceeds through a channel, which is complex. We add noise to it, which has n naught over 2 per dimension, and we get an output. We have a complex output at the end of our scaling demodulator that, if I were to zero the imaginary parts of it, would look just like a PAM system, with all signal levels having exactly the same power levels as we saw for one dimension as we have for two dimensions in this system. So ultimately, let me redraw that diagram for you, the complex channel that we're going to be dealing with. Then we can immediately draw something like this: x1 plus j x2 has some kind of transmit baseband basis function. So now everything looks low pass. Goes through a channel, which is h of omega plus omega c. That's the baseband equivalent divided by 2. And then we have noise added to it, which has per dimension just exactly what I want, variance n naught over 2. And this we can call y tilde bb if you want at the output of the system. Okay, so that's kind of a nice system to begin to analyze. If I had PAM, I'd just go in here and I'd have no imaginary part here. I wouldn't have to demodulate I wouldn't have to translate the transfer function down to DC because it's already there for PAM, because that's kind of zero carrier frequency to begin with, so it stays in the same place. And I would have had noise that would only have been one dimensional and had a power spectral density of n naught over 2 for that one dimension. And I would have an output from the system. Okay, so when QAM is used with this approach, x2 is not equal to 0. And I have complex signals everywhere. And when PAM is used, x2 is equal to 0, and I have real signals everywhere, so I can zero all the imaginary parts. So now I have a common format to describe a filtering effect in a channel for both of the two most heavily used transmission formats of PAM and QAM. And incidentally, if I want to do a map detector, whether it's complex or real, if I were to return back to chapter 1 and insert complex numbers everywhere in all the analysis, which is real there, the only thing that would change is that if that filtered basis function we're dealing with here, let's suppose we call this phi p, this aggregate, then I need to go through a match filter in the receiver, which is t minus t, reverse the the function in time, I have to put a conjugate on it for the inner product to work right. When you have inner products with complex signals, it's not one just times the other, it's one times the complex transpose of the other for inner products. So that would otherwise all look the same other than that one minor modification. And that's what I could do to do a map detector if I had isolated transmission. And again, the complex conjugate arises simply from inner product definitions. If you look at complex signals, instead of getting x of t integrated times y of t over all time, you have to put a star on the second function, which you could also write as y star times x. If you had both of these represented in terms of a set of basis functions, then you would have the complex transpose of a column vector as a row vector. Okay,